Excellent, yes. So now, as we said last time, we have all of the data that we need, and so now we can actually start trying to build the three-dimensional field theory, in particular the three-manifold invariants, from this ribbon category that Andre constructed. So that is, our goal is to actually build this extended three-dimensional field theory. And how are we going to do it? We're going to just kind of implicitly, the way I've been talking about things is that I've been saying what happens on these little elementary pieces of surface and three-manifold and such. And so more explicitly, we want to build this by describing what it does on generators. That is, generators of the Bordism category. So we need to have some idea of what it means for some different manifolds to generate the Bordism category. So to do that, first of all, we're going to back up to two manifolds and talk about how we might get generators for two-dimensional manifolds. And to do that, I'm going to talk about linear decompositions of two manifolds. And all this particular approach to, the TFTs we're going to build, as I mentioned before, are quite classical. This particular way of thinking about them is stuff that I've thought about with Chris Schaumer-Priess, and I wanted to be sure to mention his name as well. So what is, well, let me give a silly definition first. So a linear decomposition of a two-manifold, say M2, is just a diffeomorphism from a two-manifold to some particularly nice kind of manifold. So it's a diffeomorphism from M2 to some other manifold I'll call P, where P is a linearly presented two-manifold. Of course, this definition doesn't tell you anything until I tell you what a linearly presented two-manifold is. And, well, what's the idea? The idea is just it's going to be a union of kind of the basic little bits, pants and copants and unit and such that we've been drawing on the board this whole time. So a linearly presented two-manifold. Let me just say it this way. It's a union of some ordered list of these elementary pieces, the cup, the cap, the pants, and the copants. And by this, I mean really like I pick one as I've drawn it. And so I have, a unique choice. And in fact, really, I mean, as you'll see, by selecting one, I'm going to allow myself to add a bunch of cylinders on the side of whatever I've selected in order to be able to glue them together. So, for instance, say my list consisted, well, I'll draw an example in a second. So let me just finish. So it's a union of an ordered list of these along some combinatorial identification of the boundary. Okay, so let me just give an example. I think it'll immediately make clear what I mean. So for instance, suppose my list was that the first element was the pants and the second element was the copants, then I take my standard pieces and then I can identify the boundary according to any permutation, so I could kind of implicitly identify by some permutation, and so that's my resulting surface. Or if I'd done something different, if my first element had been the pants again, but I let myself add, say, a cylinder, and then my second element was the co-pants here, and I would add a cylinder here, and then my third element might be the cup, and I'd add a cylinder down here, and so then I might take just the trivial permutation to identify them and build a surface like that. So anyway, this might seem a little technical, but it's just a way of getting a very clean, precise handle on two manifolds and how you decompose them into these elementary bits. And so then you just want to show that every two manifold admits a linear decomposition. This whole story is kind of just warming us up for the three-dimensional case, as you might imagine. So what's the idea of the proof? Well, basically, we just use Morse theory. We start with an abstract surface, and we're going to pick some Morse function on it. So you sort of pick some generic map from the surface you started with to R, say. And so then the image of the singular locus looks like the following. So I have a bunch of isolated critical points, and I arrange them so that they all map to different points in R. And then what can I do? I can kind of chop up my surface into these little bits and look at the pre-images of these bits. And I can, in fact, pick a gradient-like vector field to get some preferred diffeomorphism from those little bits to standard pieces. And then what's left is some diffeomorphism along the boundaries between the cuts, and that's what leads to this combinatorial identification. So anyway, this is just meant to give kind of a rough idea. So let me just say Morse theory, ... And there is my example. So then kind of a note for later that we don't really need right now, but ends up being quite important, is that a linearly presented two-manifold has a canonical bounding three-manifold. Namely, the one given by just filling in these by the obvious surface that's inside in the way I've drawn them in R3. It's the easiest way to think about it. And in fact, that bounding three-manifold kind of comes with a projection to R2 just by drawing it in the board as I have. Okay, so that's kind of the warm-up. So now what we really want to do is know how to decompose three-manifolds. So the idea there is to do planar decompositions of three manifolds. So the definitions are quite parallel. So the first one, again, is just kind of silly abstract things. So a planar decomposition of some given three-manifold is just a diffeomorphism to a particularly nice one, namely a planarly decomposed three-manifold. And then I need to tell you what a planarly decomposed three-manifold is. And it's going to be the same sort of thing, except instead of mapping down to a line, we're going to map to the plane and chop it up into tiny little bits. So unfortunately, it's a little more elaborate to say, but let me say it quickly nevertheless. So a planarly presented three-manifold Actually, maybe I won't give a completely full, precise definition. I just want to give you a sense of what's going on. So is an ordered list of, let me call them planarly presented three-manifold strips. And then I need to tell you what a planarly presented three-manifold strip is. And I'm going to do that in the same way I did here, essentially by just giving you a list of them. So the way you should think about this is that I'm going to give you a particular collection of three manifolds, and then you're going to get to glue them along in horizontal pieces, and each one of these is some strip three manifold. So a planarly presented three-manifold strip is the Bordism. Yeah, so it's the Bordism obtained. So what are we going to do? Along each vertical line, we're going to have a linearly presented two-manifold like these, and then we're going to modify them in certain elementary ways. And a single elementary modification is going to give us one of these single elementary strips. So a planarly presented three-manifold strip is a Bordism obtained by modifying a linearly presented two-manifold in exactly one of the following ways. And now, then, there's quite a bit larger list of things, as you can imagine. So now we're going to continue this up here. So now what are the elementary bits of three-manifold we've been seeing? Well, we saw that there's a Dane twist. So if I have a cylinder, I can do a Dane twist on it, say this right-handed Dane twist, and then there's the inverse. Or we saw that there's a braiding, so I can braid like that, or take the inverse braiding. And I can do the same thing upside down for the braiding on the copants. If I had taken a manifold where I took a unit and then took its product, I could just have done nothing instead. So this is just some diffeomorphism. And so in all these cases where I'm just drawing a diffeomorphism, I'm really thinking about the mapping cylinder of that diffeomorphism as the three-manifold, as we've been doing, and the inverse there. And similarly, if I had the unit map on the other side instead, then I have the associators. For the product operation, and similarly the co-associators for the co-product, depending on whether you're reading upside down or not. Then I have the Frobeniusators that we talked about a little bit yesterday. And then that's all the things that are implemented by diffeomorphism surfaces, and then there are some actual, if you will, honest-to-goodness three-manifolds, by which I mean ones that implement some three-dimensional, non-trivial three-dimensional Morse function. So I can take, if I had nothing, I can take a three-ball and create a sphere, or I can do the inverse operation. If I have a cap and a cup, I can do surgery to glue them together, or the inverse. If I have two cylinders, I can do surgery to glue them across the middle. And then finally, if I have a hole in a twice-punctured torus, I can fill in that hole to get a cylinder, or conversely, I can punch a hole through the middle of the torus. And that's it. So that's the end of the definition. And so what you should think is that these are kind of the three-dimensional generators. So now you can start to get a sense of what I mean by generators of this two categories. So there's just one generating object, the circle, and then there are these four generating two morphisms, and then there are a whole bunch of generating three morphisms. Sorry, I meant objects. Generating object would be the circle generating one morphism and generating two morphisms. Thank you. Okay, and so then the proposition is that every three-manifold actually admits a planar presentation, a planar decomposition. Okay, so that's good because we want to know that we can evaluate. If we go and try to define some invariant by specifying it on all these generators, we want to know that we can actually evaluate it on any three-manifold we want. And so just very briefly, the idea of how you get a planar decomposition is you sort of pick some sufficiently generic map from M3 to R2, and you can kind of look at the singular locus, the image of the singular locus in R2. It's going to have some lines, and they move around, and those singular loci might have cusps, and they might have crossings in different places. So it looks something like that. And then what you do is you kind of chop it into strips so that horizontally there's only one thing happening in each strip. So here I've chopped it so that the first thing that happens is that I have this line, the singular line that turns around, and then I have a crossing, and then I have a cusp, and then another turnaround. And then once I have each of those strips, I can go and try to check that each one is implemented by exactly one of these little pieces. And very roughly speaking, what you see is the following. So if I have these little if the singular piece looks like a cup or a cap, that's when the real three-dimensional Morse stuff is happening. I might want to name these. So this is nu, mu, eta, and epsilon. And so those correspond to these Bordisms and their opposites. If I have a cusp going either direction, those correspond to these unit lambda and rho. These are just the unit and co-unitators, or whatever they're called. If I have a crossing, that's the kind of thing that corresponds to something like the associator or the Frobenius ator, where I had two critical points and then they moved different levels vertically. You can sort of imagine those are like these two singular lines crossing. And then if you don't see anything, then what can happen is that you can have a Dane twist sitting there. And if you just see a line all by itself, there can kind of secretly be a braiding. So there's some information that's not contained in this picture that you kind of deal with at the gluing lines. Okay, and there's sort of a corresponding note for later here, namely that a planarly decomposed three-manifold has a canonical bounding four-manifold. Yeah.
This is some kind of non-trivial generalization of Morse theory. So, for example, how do I know the critical points are lines and
Yeah, definitely. I mean, this is what these days goes under the name two-Morse theory, if you will, because instead of projecting to a one-dimensional thing, you're projecting to a two-dimensional thing. So it's definitely, I mean, it's in the same spirit, but you need more technology to do it and so on. It's not so different than what used to be called surf theory, because in fact, when you're doing one-parameter families of Morse functions, which is something surf studied, then that's related to, though not exactly the same as what's going on here.
are those critical lines closed or what kind of things can happen?
Yeah, they're very well, I mean, we sort of pick things to be such that they're very well behaved. Yeah. So this this bounding four manifold just comes from taking the same filling of the linearly presented two manifolds and kind of stretching them along as you go through here. And this is something Andre and I just realized this past week in Rio, but has been very useful, as you'll see. Okay. Oh, well, I guess maybe I try to stick it on over here. I mean, somehow the actually maybe slightly surprising theorem sitting here is that there exists a finite presentation of board 1-3. The fact that you could produce a presentation like this isn't really so surprising, but the fact that it's finite is something it's a priori obvious that you can achieve. So for instance, when we talked about the boardism 2-3 category right at the beginning of the workshop, I said, well, you have some infinite list of objects and then some infinite list of morphisms, and I mean, there's just no way you could obtain a finite presentation in the sense I'm thinking about. And so so this is a precise sense in which going down to circles made our lives much better, is that we turned what was an infinite problem into an explicitly finite problem.
Is there a way to relate this presentation to more familiar presentations like, I don't know, regard splitting or anything else?
Yes. But it's not obvious, and this is also something that Andre and I just figured out this week, is exactly how you do that translation to surgery presentations, and then from there you can go to... Yeah. Okay, continuing on. So, what time did we start? I didn't look, just so I have a sense. Okay. Okay, so then where are we? So our task then is to actually, so we're given C, which is going to be some ribbon category, namely the ones we've constructed, and we want to define the some functor Z on each of the generators. Of this boardism category. And so which ones have we done so far? Well, the pants and so this is just part of the underlying tensor structure, and the copants and co-unit I already described are determined as adjoints to those maps. The twist and the braiding are part of the ribbon structure that were just provided. The unit on each side is, again, just part of the structure provided. The associator, we didn't talk about it very much, but it's just provided by the tensor category itself. So all we're left with is needing to define the Frobeniusator and these three non-trivial four-dimensional morphisms. Okay? And so it's in describing those that it's really convenient to use this internal string diagram notation that we discussed a little bit yesterday. Yep. It is, yes. That's actually... It could be. It could be, yeah. But it's not.
How many are there? How many relations?
Yeah, about the same order as the number of generators-ish.
13 relations.
Okay. Where are we? I guess I better say, so let me just review. I said I would review this internal string diagram story a bit. I sort of remembered what they're called in literature. I think they're just called fields, classically. But anyway, maybe a physicist could tell me. Okay, so recall that I was sort of saying that a functor, so we're trying to encode some functor from, say, z of one surface, s, or say sigma to z of some other surface, sigma prime, encoded by some three-manifold, and we want a way to describe that functor. And so the claim is that these functors are encoded by, oh, sorry, I've screwed up slightly. So that thing would be a natural transformation between two functors, and those are encoded by maps of vector spaces. And what are those vector spaces? Well, the functors on each side are encoded by those vector spaces themselves. They're sort of called the structure vector spaces. And so if you have some surface with some topology, and I label the incoming, outgoing things by simple objects, I, J, K, M, and L, then the vector spaces that determine this are Hom in, say, C tensor C from M tensor L to, well, let me be really clear and use a different symbol. So I'm going to use the external, this sort of square box to denote the external tensor product when I really have two separate copies of the circle. So Hom in C tensor C from M tensor L external to the image under this functor of I tensor J tensor K. Okay, so this is just what I said yesterday. I happen to have written it down for a more complicated surface than I did then. But the claim is the same. The claim is that these vector spaces, as the indices run over all simple objects, actually determine the entire functor, and that to give a natural transformation between functors is just to give maps on these vector spaces. And I remind you that the claim is that this vector space is, again, formal linear combinations of these internal string diagrams mod some equivalence relation where you let yourself move those diagrams around. I see a nod from Raimundo, and he looked so quizzical yesterday. Oh, I see. I see. You're not going to let me skip it again today? Okay, I'll see what I can say. Okay, so I'm going to, okay, just very quickly, I'll just say by drawing, again, what is an internal string diagram? Well, it's the kind of thing where you have lines labeled by some objects, and then you have nodes that might wander around, and then at some special places, there are these things called coupons, which I'm drawing by little boxes. And these things move around up to isotopy, and inside each coupon, there's a morphism from the tensor product of the things on top to the tensor product of the things on the bottom. That's just what one of these is. And I'm allowed to, if I have a situation where I, say, have one coupon and then some other coupon in any kind of configuration, I'm allowed to change my sting diagram by putting a giant coupon around, actually composing the morphisms given by all the sub-things. So if this was labeled F and G, I'm allowed to actually compose these morphisms and then put whatever the result is, that morphism H, as the label on this new big coupon. That's part of the equivalence relation that I apply here. Okay, so that's to give you an idea. And then there's certain special, if your category is equipped with some extra structure, they're kind of special coupons. So for instance, if your category is braided, there's a special coupon denoted like this. What this is really, as a string diagram, it's a 4-valent coupon, and the label is the braiding morphism. We just don't draw it. And similarly, a cup is really a special kind of 2-valent coupon that looks like that, and it's the evaluation map of those two objects. And similarly, that one, and then there's one last special coupon. If it's a ribbon category, then there's this coupon which we actually just labeled theta, or Andre drew it with this notation, with this twiddle notation like that. Okay. I think that's all I need to say about that. Okay, so Raimundo wanted some idea of the proof. So briefly, so it's the proof of this equality there. So the first thing you do is you check for the elementary pieces. So I just erased the 4 elementary pieces, but you go through and check for each one of those. And let me do just one of them to show you that there's something slightly, very slightly interesting going on there. By the way, I should definitely mention, I learned this stuff from Jamie Vickery, and somehow always avoided this perspective on things until he convinced me that it was the way forward. Anyway, so this this copants operation is encoded by these vector spaces, which I'll denote I, J, K, which is defined to be HOM in C tensor C on the top from J tensor K into Z of the copants applied to I. So I'm sticking I down here and J and K up here. And so I need to convince you that this is the same as the set of internal string diagrams. So there's only one move here, which is that how was Z of the copants defined? Well, I defined it to be the right adjoint to Z of the pants. So I can rewrite this as HOM in C from Z of the pants applied to J external tensor K to I. Well, what is Z of the pants applied to this external product? Well, that is just the actual product in the category of J and K. So this is HOM in C from J times K to I. And what's that? Well, what are the string diagrams you can put in here? Well, they all just look like something with one coupon. And what is that coupon? It's a map from J times K to I by definition. So this just is the internal string diagrams in the copants. Okay, so it's a very easy computation, but it used the way that we had defined the copants. Yes? No, okay. And so then what's left to do, so then you have to show, you essentially have to show that these things compose nicely, that if you take the internal string diagrams on one surface, say S2, composed with another surface, S1, you need to know that that is the sum over all the ways of labeling. So what's the picture here? I have one surface, and then I'm gluing it to another surface. This is S1, this is S2. There are a bunch of different ways I can label the cut circles by simple objects, and I need to sum over all of the string diagrams that do that on this one surface, tensor the internal string diagrams with the other set of labels on the other surface. This is from labels I to K. So anyway, you just need to check that these things compose well, and let me not say anything about that. You can think about that. This is not meant to be difficult. Okay, so now that's that. So now we can actually do it. So now we just need to say what all these maps do on internal string diagrams, and then we'll at least have a candidate for a three-manifold invariant. So let me say some of them in words just to save time. So, I can just draw them right on this picture. Fantastic. So, which means I can do them quite quickly. I forget what color I decided to use yesterday for internal strings. I'm going to go with green today. So if I have something like alpha, where somehow this diffeomorphism isn't really doing anything in our in the way we've presented it, you just stretch everything around without changing the topology of the string at all. So you just do something like that. And similarly for these units and co-units, if I have something like this, so by a little dot, I just mean this is if I have the unit object, if a string is labeled by the unit object, I can just erase the string because it doesn't affect anything. And so if you see a line just ending in the middle of nowhere, it means you had a morphism to the unit object. Again, you just don't change the topology at all when you do whatever the thing is. So that was a picture of lambda going that way. So those are those ones. I drew, so the Dane twist, I drew yesterday. If you have a string running down the middle, you just attach this. You apply the twist in the category to that object. And if you have a braiding like this, then you do something slightly more interesting, which is that you introduce an internal braiding and then let the ends run down like that. Okay, so now we're left with these 5 more interesting ones, so I need to tell you what those do. I think maybe I need to draw those bigger. So let's define the Frobeniusator. Oops, sorry. So suppose I have an internal string in here. It's going to look something like this. So in this very weird perspective where both the tops and bottoms are visible, sorry about that. So by dot, I mean there's some morphism labeled there. I'm just not giving it a letter. So there's always some label running around. And so I need to tell you where this goes under this diffeomorphism. And I already mentioned a special case of this yesterday, but it's useful to redraw. So I put my 4-valent vertex in the middle here, and then I twist everything else around. So it's kind of the minimal thing that you can do and still have it fit in the new surface. But as I mentioned yesterday, it required the existence of duals in the category to even make sense of these internal string diagrams, because I really implicitly used these special evaluation and co-evaluation coupons. And the reverse one doesn't do anything. It just, when these surfaces push away, it just leaves whatever diagram you had unchanged. So I won't draw that one. So now, more interesting are, yeah. Yes. Yes, yes.
You could have started from another string diagram with only 3 lines crossing, right?
Sure.
And I'm not sure if I understand which string diagram are you using, because you can have several.
So I'm not sure what kind you're imagining. You're imagining
That's a good one.
one like this.
The other one also, but that's perfect.
Yep, so the nice thing is that if I started with a string diagram like this, I can re-coupon it by just sticking a giant coupon down in the middle like that, and then whatever the actual composite morphism was of all these things inside the category, I relabel, and now it looks like one of the kind I had. And so that's why I only told you what to do with these ones, is that actually every string diagram for this surface has that form.
But on the other side, you seem to be using more coupons. So you have co-evaluation on one side, and you have a lot of coupons there.
Yeah, there are 5 coupons there, exactly.
Why is it that you are forced to use more than one?
Oh, well, because this surface really has this complicated external tensor in the middle.
Can't I just move this 4-value point just so?
Oh, you could, yes, sorry. I mean, you could move this 4-valent point up to here and then get rid of a whole bunch of those coupons, but I prefer to draw it this way because it's more symmetric. Okay, so let me tell you the last few. So, okay. So, okay, so now I'm going to define these, whatever I called them, nu, mu, eta, and epsilon. So nu, oh, well, I should tell you what the strategy is before I just write down a bunch of stuff. The idea is that nu, mu, eta, and epsilon are actually the units and co-units of the adjunction that we used to determine this and the co-unit as the right adjoint to the pants and the unit. And so we ought to be able to pick them to be, as long as we pick them in a way that satisfies the adjunction relations, we ought to be able to pick them to be whatever we want. And so you can just make a choice and write it down, which I'll do right now. So there are no strings, so this completely specifies that morphism. If I had some strings there, when I glue them together, I don't do anything. I just leave them as they are. Similarly, if I have 2 cylinders and I glue those cylinders together, I just leave those as they are. And finally, if I had some string diagram, oh, sorry, it should have been in green. I guess I'm drawing them all in white. Sorry about that. So if I had some string diagram in that picture, then I just, and I'm filling in the hole, I just leave that string diagram as it is. So these were all very easily. I basically didn't do anything. Yes? Oh, thank you. Yeah, and these all should have been little maps too, just to keep track of what's going on, because I'm really describing a map just recall what these pictures mean. It really is describing some element in a vector space, and I'm telling you where that element in the vector space goes. That's what these pictures mean, and together all those maps encode the... maybe I'll leave that stuff up for a minute. Yeah. Yep.
Right? And you still get a connected something without a hole.
Yep.
So the string diagrams there there's only one figure, but your coupon has a label that is any morphism.
Sorry, here you mean?
Right. So there's only one string diagram that I can draw that is just essentially the one that you have in the Frobeniusation.
Sure.
There. But the label at the point is just any morphism.
Oh, you mean in the middle? Well, what you said isn't maybe wrong, but I would have said it differently. If I want to recoupon this thing to look like that, then the morphism is the identity from this simple object tensor that one to that tensor that. It's just I tensor J goes to I tensor J by the identity.
So that's the particular one that you're choosing?
Yes.
I'm referring to the original theorem.
Oh, sorry.
So in the theorem, the proof of theorem,
Yeah.
then you're allowed to use any morphism as a label for this coupon that you would put there.
Sure, yeah.
Okay, so you're adding
Yep. Okay, but now I need to, I need to quickly tell you what happens to the morphisms going the other way, which are more interesting. So let me draw those. So if I start with the sphere here, and where are these? Oh, maybe that's not the one I want to start with. Let me start with the cylinder and cut it in two. You see, they're more interesting because we can't leave things alone anymore. If I have some string running through here, I can't just do nothing. I've actually chopped the surface off. I've got to do something to this string. And the answer is that if this string has a label I, if I is not equal to the unit object, then this map is 0. And to encode that, I'm just not even going to tell you what it does when there's any string at all in here. And so I only say what it does on the empty string. And in that case, it goes to this empty manifold over here, except it's multiplied by some non-trivial constant p, which we don't know what it is yet. The idea is we're going to try to figure out, although we're not actually going to succeed today. And similarly, if I have the sphere, I need to send it to the empty manifold. Again, what do I do? Well, this has to be in a certain adjunction relation to this one, and you can check that this has to be the constant 1 over p. And there are only two more. So if I have a, okay, I need to tell you what, say, epsilon is. So, epsilon op. So if I start with this cylinder and I want, so I have some string running through it, and then I try to punch a hole in that cylinder, what happens? Well, let me use color. So that string still sits there, but then I end up with, so say this was labeled by I still have that string labeled I, but then I have some other string labeled J, and then I sum over the quantum dimension of the object J divided by P. Now, you might wonder where on earth that came from, and I was actually planning to tell you, but I don't think I have time, so I'm happy to chat afterwards if people want. I'm just going to ask you to believe this formula, and this is maybe the first place where, on my side, I sort of needed these quantum dimensions that Andre just explained to us this morning. And
does it come from the Frobenius glue then, and then you have to get this picture?
That's one. That is one approach to getting it. Another way. Yeah, I mean, there are a few different ways to figure out how these numbers are related to the quantum dimension. Another way is to realize whatever this map is, it is in a certain adjunction relation with the one where I sort of am going to snip this edge. And that snipping procedure is going to only be able to occur if there's nothing in the middle. And so if I have some strands running through, I need to get rid of them. And the way to do that is to kind of take some trace of them to get rid of them. Okay, and then there's one left. What's the one that's missing? This one. So I need to tell you how to go from here to here, how to chop these apart. And this is, again, a bit more complicated. So I have some morphism in the middle here, and I should have left myself quite a bit more space. So this whole thing goes to, so say these are labeled I, J, and J. If these labels aren't the same on the top and the bottom, the thing maps to 0. And if they are, then it maps to this constant P over the quantum dimension of the object I times the quantum dimension of J times the numerical constant I get by evaluating this string diagram where I have some morphism and I take the trace on both sides times the identity string. Okay, so I'm realizing that this was a lot, but hopefully it gives you a sense, at least, that you can just explicitly write down what happens. So I've now told you what happens on every generating 3-manifold. And to make sense of it, I suggest we just dive right in and actually compute the value of the TFT on some 3-manifold, since that's what we wanted to get to. Yep, I was about to do that. Thank you. So the gap is saying what P is, and so the claim is we can take P to be the sum of the DI squareds over all the simple objects of the category. So I'm summing from, whatever it is, 1 to n over the simple objects of the category, sometimes called the global dimension of the category. So let's do some examples. Of the invariants coming out of. So the claim, obviously, is that this produces some field theory. So let's see what examples we want to do. So let's do, maybe I should be a little more precise. I mean, the claim is that this produces some field theory. And so the idea that, right, the idea is that this produces a field theory, but it doesn't depend just on the 3-manifold. It actually depends on the 3-manifold together with this canonical bounding 4-manifold that I mentioned earlier. And and so, this is, again, well, I'll leave it at that. I mean, this is all kind of, again, leading to this field theory that was known to Reshtikin and Turayev and Witten before them and so on. But this particular presentation of it, comes from discussions with Andre and with the other people I've mentioned, Chris and Jamie and Bruce. Okay, so let's do some examples. So what's a good example? So that one example is complicated. Let's do the simplest example I can think of, S3. And I'm going to call this S3 version 2 for reasons that will be clear in a minute. So I can start with the empty set and then create a sphere and then kill the sphere. Okay? That certainly gave me S3. I just took a 3-ball and glued on another 3-ball. I got S3. What invariant did that give? Well, if I start with the empty string diagram, it goes to the empty string diagram, and then I map to the empty string diagram, except that I picked up a factor of 1 over p in this very last map. So this whole thing evaluates to 1 over p. So 1 over the global dimension is the invariant of S3. So that's kind of boring, but let's try a more interesting example. So let's try, well, maybe we have a minute to do a more interesting example. So let's try to compute the invariant of the 3 torus. So you have to think for a minute to actually come up with a presentation of the 3 torus in these terms, but I'll write one down, and you can think about it. So first I create a sphere, and then I punch a hole in it to get a torus, and then I take the 2 legs of the torus and pinch them together in the middle to get a genus 2 surface, and then I cut that genus 2 surface off in the middle, and then I kind of reverse that whole procedure. I merge them back together into a genus 2, and then I glue the 2 holes together to get a genus 1 thing, and then I kill the hole and then go back to the empty set. So let's see what this does to our string diagrams. So this stage, this was the first interesting one. I picked up a sum of di over p, and then a loop labeled by I. And then I merged them together. That didn't do anything, so I still just had the same sum di over p. But then I chopped them in the middle, and so that was quite an interesting operation related to what we were mentioning earlier. So when I chop them in the middle, I need to think about what to do to this situation labeled by I and I star. And it turns out that this morphism in any category with duals is equal to 1 over... Yes?
Change the color.
It's invisible. Is that better? White is better. Okay, you want me to stick to white. Okay. So this is just a little side computation, which is that if we have I star I, we can write this as 1 over the dimension of I times the cup and the cap, plus some other stuff that doesn't factor through the unit object. And so when we actually do this brutal split, it doesn't kill this factor, but it kills all this other stuff. And I'm worried about a factor of p. Maybe I needed a factor of p here, too. Shoot. Oh, no, it's okay. So this operation where I stuck 2 legs together, where did that happen? Well, that happened... Oh, no, that didn't have a factor of p on it.
Can you just make a cylinder? You have the 2 torus here, so that doesn't add a p, but then you need to use this from the... you just first glue those 2 lines, and then you use this factor of p that you're getting from the last board.
I'm not sure. Were you just talking about this morphism?
Yes,
or?
in that morphism, there's a factor of p that will appear.
Oh, fantastic. That's what I wanted.
Well, because you just have a cylinder between the 2 torus, just draw one big cylinder, right?
Yes.
Just first merge the 2 lines.
Thank
then
you.
Use the morphism that is first in this board.
Exactly. Perfect. So that cancels out this p, and then this di cancels out that di, and we're just left with, writing in white, this sum. Those are labeled I. These are labeled I as well. So now there are no more factors. And now we glue back together, and once again now that doesn't do anything. We just have, again, these two sums, I and I. And now we chop down the middle, and that does do something that gets us to the sum of P divided by di times the sum over I. That was actually, again, now some small computation using those formulas. And then finally, what's this very last step? Well, we just remove this middle dot, and we're left with just a circle with I. So that's the quantum dimension of I, which cancels this di. And then, so then we're left with, I guess, the sum over of P. But then we're going to have 1 over P, I hope, this very last stage. And so we end up with just a sum of the empty thing. This is over all the simple objects. And so we conclude that the invariant of the 3 torus is equal to the number of simple objects, which is sometimes called the rank of our tensor category C. And that might even ring a bell with some of you. Okay, so that's the kind of thing. You can try it on other surfaces. So the reason I called this S3 version 2 is that there are some other examples. So I mentioned that the invariant you get depends on the bounding four-manifold implicitly. And so you can present S3 in other ways. So for instance, I won't do the whole computation, but I'll just show you what you could do. So you could take S3, and then you could punch a hole in a sphere, and then you could do a Dane twist, say, along this one leg to get back to a sphere, and then you could fill in that hole to get back to a torus, and then you could fill in that hole to get to a sphere in the empty set, and you can check that that also produces an S3, and you could compute the invariant, and you'll see that it's different than the invariant you computed here. And so you really can see exactly the way in which this invariant depends on the bounding four-manifold. But, let me just write down the answer because it'll be useful. So the answer here, so maybe I'll leave it as an exercise in these string diagrams, so is to check that you get what do you get? You get the sum, you get 1 over the sum of di theta I inverse. That's actually not that's not the obvious thing you get. Requires quite a lot of translation to get to here. So that sort of made the exercise quite a bit harder by writing it like that. But this quantity down here is something called P minus. And so just to finish up, if you want to, you can actually instead produce invariants of 3 manifolds directly that don't depend on the bounding four-manifold just by getting rid of the difference we saw here. So we had 2 different presentations of S3. We got 2 different invariants. They happen to differ by some numbers. P was, P is what I wrote over there. And again, these are, I'll talk about it more in the next lecture. So these differ by some concrete number, and you can just correct for that number using global information about the bounding four-manifold. And so, yeah.
The number depends on the presentation,
This number you get, yes. Well, it doesn't depend on the presentation. You then need to check that it only depends on the bounding form manifold, not on the presentation. Yeah. Exactly. But I mean, that statement contains a lot of work because you have all the different relations among the different presentations, and yeah. Okay, so maybe I'll just write down the formula and leave it there. So you can define, so now I'm going to define Z-twiddle, which is no longer a field theory, but is going to be a three-manifold invariant. So I'm going to define it. So I'm going to input, let me denote by this pair, perhaps confusingly, I'm going to denote it as one of these planarly presented manifolds, just so I know how to apply my procedure as described here. Then what I can do is I take this unfortunate difference that I found over there, and I take minus the signature of the bounding form manifold, and then I multiply it by the value of my actual three manifold, my TFT invariant, and then the claim is that Z tilde only depends on M3 itself. And so Z tilde is actually the Reshtikin-Triav invariant of the three manifold. And so conceptually, what's going on, you can kind of argue about which thing you like better, Z or Z tilde. Z has very nice gluing properties. It has these sort of TFT gluing properties. You can understand the big thing in terms of small things. Z tilde does not have good gluing properties. But it has the advantage that it actually only depends on the three manifold itself. So kind of half a dozen of one, 6 of the other. Anyway, I'll stop there.